Alrighty. Hello. Welcome to another video. Today we're going to be talking about like terms and combining them, and why you should not combine unlike terms, what are terms, what are unlike terms, and all of that sort. So if you're here for any of those questions, definitely stay tuned. So when it comes to like terms, first of all, we have to explore what does the word terms even represent in math. Well, in another video, I detailed what we call the order of operations in mathematics, often represented by the acronym PEMDAS. And essentially what that says is if we have an expression like, let's say, 1 plus 2 times 3 squared minus 4 over 2, something like that, then what we must start with in order to do things and have it pop out as the true value of this expression is start with the parentheses, do everything inside the parentheses. And then, well, first of all, let's look inside the parentheses. We have some operations such as multiplication and addition. If we look down the hierarchy of priority for operations, we see that we have multiplication and addition. Multiplication is in a higher level. Notice that multiplication and division are in the same level, and so are addition and subtraction. But multiplication is higher than addition, so we do the multiplication first. We get 1 plus 2 times 3, which is, of course, 6, which would simplify this guy. Now we only have addition inside the parentheses, and so that guy would become 7. And then, of course, we still have this 2 up here. This is a square, it's an exponent. Now that we're done inside the parentheses, we now move to the exponent, which is on the outside of the parentheses, and we can then square 7 to be 49. I'm going to go ahead and add a 6 here, just so we have multiple different terms, and I'll talk about that in a second. Here we can then subtract 4 over 2, which in this case, division is higher priority than is subtraction, and so we can divide first. We get 2 and then plus 6. So now we're left with 49 plus 2, or minus 2 plus 6, and to pay special note to the the addition and subtraction that was here at the start, those are still remaining at the end here. This addition right here was within the parentheses, so we kind of still wound up doing that first, but the addition and subtraction that was just in the main problem are essentially the lowest priority things. And when we simplify all of these guys, these big chunks that are separated, if you imagine we have like a wall here between all of these main parts that we handle first, these individual spots I like to call terms. Those are our terms of our little expression here. Things that are ultimately separated by addition and subtraction. Now, it just so happened that this whole expression had 3 terms in it, and all of them happen to be what we call constants, or constant terms. Now, if you think about what the word in English means, the word constant, it is essentially unchanging. It stays the same. Well, this number right here, 49, is and always forever will be exactly 49. Same with negative 2 here and this positive 6. Those are numbers, and they are always going to represent the exact same thing, at least in our number system. Now, what is that opposed as opposed to what? That kind of implies that some things are variable terms. Now, what are variables? Well, examples may include things like I'm going to make a list: x, y, z, alpha, beta, gamma, epsilon, e, l, k, p, q. Pretty much I'm listing a bunch of letters out. Smiley face. That could be a variable, as long as you use it to represent essentially not something that is not a constant. Something that varies in terms of its actual value. Now, of course, if you're going to do something like draw a picture like a smiley face, you might want to say, hey reader, whoever's looking at this work, these smiley faces are being used to represent essentially, well, I'll explain what a variable is right now. A variable is kind of like a placeholder. This smiley face over here might be used to represent, if we have an expression such as, I'm going to switch colors actually when I write this. If I were to have, for instance, x plus 2, the value of this expression depends. It varies based on what exactly I choose for x. If I let x equals 2, this expression becomes 2 plus 2, which is 4. If I let this guy be instead 3, this becomes 3 plus 2, which is not 4, but 5. And so the expression ultimately changes depending on what I choose for x, and until I specify what x is, we can say x will vary. It might take on any different value. And especially if you see something like x plus 2 equals y, then these vary together and they depend on one another. If I say x is 2, then y is 4. If I say y is 4, then x is going to be 2. You can kind of solve for one another. However, solving is not going to be something that we talk about in this specific problem, or in this specific video rather. It's instead going to be dealing with like terms and seeing about adding and subtracting them. And of course, note I say adding, subtracting them. Here again, terms were broken up by addition, subtraction, the lowest priority thing. And so we are going to then discuss. So here we were able to combine these like terms. These are all all constant terms here. The 49 minus 2, which is 47, add 6 to get 53. We can combine all those terms. However, we cannot combine what we call unlike terms. For instance, x plus 2. This guy x, this is not a 1, it's not a placeholder for a 1. I mean, there is one x here, but we don't treat it like 1. Because if we did, look what happens. We would then, if we were trying to combine those, we get, okay, well, if we're treating it like the number 1, then we get 1 plus 2, which is equal to 3. But then if x is equal to 5, then we get 5 plus 2, which is equal to 7. But hey, these are not the same thing, so therefore we kind of messed up. We treated like x was the number 1, and so it led us to being equal to 3, but it's also equal to 7 if x is equal to 5, so it's kind of confusing. We could also, imagine, I've had some people say like, oh, I want to try going x plus 2 is like 3x. Well, if you do that, we have, well, this is equal to 3x, but then if I plug in, say, 5 to this guy, the initial expression, so I'm going to erase that, I'm going to put that right here, 3x, then we have 5 plus 2 equals, well, 3 times 5 is 15, which is 7 equals 15, but no, it in fact does not equal 15. That's, do not do that, because you do not get what you would like. You get something you do not expect. These are not equal. You get a little contradiction in terms. You find that the same expression, or what you thought was the same expression, gave you two things that are entirely different. So that's talking about adding, subtracting variables versus constants. You cannot add and subtract them because that gives you you might get a scenario where you have like 7 equals 15, which is something that doesn't make sense because 7 does not equal 15, because that's kind of how we define counting in numbers and whatnot. So it kind of violates what we know ahead of time in our foundation of math. All right, so that kind of helps distinguish in terms of like adding, subtracting constant and variables. But what about adding and subtracting variables of different types? For instance, could I add x and y? Well, if I did x plus y, first of all, what would I write? Would I write like xy? Would I write like just 2x or 2xy, or what would I do? Well, hopefully that's a little bit muddy there. Let's say I had this. I'll go ahead and write out what each of these would be. So if x was 5 and y was 6, these guys together would make 11. xy would make 30, and then 2xy would make 60. Hopefully you notice that this is what we started with, x plus y. That's 11. If this was what it equals, if we could add these terms like this, then we'd wind up with 30, which is not 11, so this guy is already a no-go. If it was something like this, then we'd wind up with 60, which is a no-go. And of course, if lastly we were to do something like equals 2x plus y, or 2xy, or something like that, hopefully you see this is obviously going to be different because we have a 2 in front of the x, but this would be 10 plus 6, which is 16, also not equal to 11, which was over here. This is what this guy equals. So adding obviously different letters or different variables by name in symbol will not be permitted, because obviously it leads to something that doesn't make sense. And so we say it doesn't make sense to add unlike terms such as this. So now we've talked about constants, we've talked about variable terms. However, I didn't quite go through all types of variable terms. Here I just left one symbol each within each of these little entries here. However, included in the distinguished variable types, I also have things like x squared. or like xy, or y squared, x. Now, when I put two variables together, I'm kind of meaning that I'm multiplying. I don't do this with numbers like 5 times 5. I don't write as just this because this is also could be confused with 55 or 5 times 5. And in order to avoid having that ambiguity, I say this guy without the dot is 55. If I put a dot there, it's actually 25 or 5 times 5. With variables, I use the example 8a because it kind of sounds funny. If I can't, there's no number that is like 8a. I mean, there's 80, which is pretty close, but like that's not what this is. There's no number you can confuse with that. When it has two variables next to each other, you don't need to put the dot because there's only one thing it could mean, as opposed to numbers where it would just, there are numbers that have 2 digits. Now, when it comes to adding, subtracting, combining terms with these guys, if, for instance, I'm going to go ahead and do down here x and x squared. First of all, I want to explain what these numbers are. X squared is 2 copies of x multiplied together, just like exponents, like 7 times 7 is 7 squared. It is 2 copies of 7 that are multiplied together. Same thing goes with the x's, the variables that we might see in everyday math classes. You treat the variables as though they are numbers in terms of how you write with them and like doing operations in like notation wise. Of course, you can't actually compute it because, well, what is x? Well, it could be 7, it could be 14, it could be pi, it could be negative 87.382. I have no idea what it is, but we can still write that we want to square it because we're treating it like a number. Just say like, whatever this number is, I want to square it. Well, what does that mean? I multiply it by itself. So that's kind of like what those are. And similarly, like if you had x times y, you just like whatever x is, whatever y is, you just multiply them together. Cool. So now we're going to talk about, big question is x and x squared. They both have x in it. Are these like terms? Can I add them together? Well, let's try this out. So let's say that x equals 2. And we're going to go ahead and write some possibilities for what this could equal. Maybe the rule is every time I see a copy of x, I add it together. So here I have x squared, which is 2x's. In 1x, I have just 1x. So this is equal to 3x. Or maybe you see, okay, there's 1 in front of each, so it's like 1x and 1x squared. And like whichever one has the most exponents, we throw it in there. We say like, okay, this is equal to like 2x squared. Or maybe like you notice that this is 1 copy of x here, and you say, okay, so therefore we have like 2x cubed. Or maybe you say it's just equal to x cubed. I don't know. Whatever you want to try out, you can explore. However, let's go ahead and see what happens if we specify that, for instance, x is equal to 2. Well, if x is equal to 2, this guy right here, we can just plug 2 in. What this means is we're saying 2 is the value we choose for x, so therefore this is really 2 plus 2 squared. We do PEMDAS exponents first. That would be 4 here, plus 2 should be equal to 6. Let's explore these now. 3 times 2, 6. Okay, that one might work out. Let's keep going. 2 squared times 2, well, 2 squared would be 4, and then times 2 should be 8. So clearly that's not right because 6, 8 different answers. So I can kind of strike out that guy. Here I have 2x cubed. Well, 2 cubed is 8 times 2 would be 16. So that's not looking good either because that's different than 6 right here. I'm going to clear that up a little bit. And then x cubed, well, that's just, of course, 8, which is also different than this guy. So right off the bat, we kind of knocked out 3 different answers. Now, here I made a couple of key moves here. First of all, I knocked out all 3 of these answers. So I'm going to go ahead and erase all these. It can't be any of those options. However, when I evaluated these, I chose the specific value of 2. Now, I kind of did that randomly. I wasn't really thinking about what it would look like. But imagine instead we had chosen 3. Well, if this was 3, what would this turn into? It would be 3 plus, well, 3 squared. 3 plus 3 squared is 3 plus 9, which is 12. Well, look at that. 3 times 3 is just 9. If I chose a different value of x, then this one also shows that it's not equal. Whoops, sorry. These guys are not equivalent. And so clearly, for some values of x, this is also not the same thing. And so if we assume that we can add together exponents, and same with the other 3 examples that I kind of erased that were right here, if we assume we can add the terms like x and x squared together, and you get something like this, well, that just leads you to a contradiction, because you assume that you can do this, and then you wind up with 2 different answers for the same problem. Same thing with these, but like I tested out different values of x. There's lots of x values that it could be, but if any of them don't work out, then you just get a random different answer. So hopefully this convinces you that you can't just arbitrarily, you can't at all add together unlike terms, and specifically that these guys right here are not like terms. Because if they were, you could add them together and not reach any sort of problems like we had just a second ago. So terms like this, x squared, xy, y squared x, those, as it turns out, are still numbers, because if we treat x like a number, then x times x is a number times another number, which in turn should be some other number. So these are still individual numbers when we treat them. Of course, they are like unknown numbers, but like they're yet to be specified, but they are still numbers in of themselves. And they might be the same as some of these numbers, but we don't know that either. Keyword there is might be. And so the only way we can know that 2 variables are the same is if they are literally written the same. X plus x is equal to 2x. We can do like xy minus 3xy is just negative 2 xy's. Whatever it is that xy equals, if I have one of them and then I take away 3 of them, I'm left with 2 of them. Now the fun thing about this is that when it comes to adding terms, whether you're dealing with constants or variables, the only thing you're really going to be like doing the math with in this sense are numbers, the number part. And for variable expressions, variable terms, the number that's in front we call a coefficient. And you add together the coefficients of the like terms. If I had a x squared here as well, here if that was like 4x squared, our final expression would be, sorry, I'm going to just move that guy to the right. I didn't see that for a second. It would be, for instance, 4x squared minus 2xy. The x squared and the xy are not like terms, so we don't add them together, but we can still add together the like terms. All right, just to do a quick summary, and then I'll do a couple problems. If you would like to stick around for that, you may. We have like terms, that's what we're talking about. We have an expression up here that we could simplify. The terms are the things that are being separated by the addition and subtractions. And most of the time you can break them down to individual constants or variable, or all the time you can break them down to either individual constants or variable terms. Sometimes those expressions might be a little bit messier. But it's not like here, like it's more complicated, and you might see an example like if you had instead like 1 plus x squared, and let's say you didn't know how to do this, or maybe there's just some other things that you don't know how to simplify yet. This guy could still be considered a term, or maybe this is not the best example. Ignore me. So just know that it could be a little bit more complicated than what you're dealing with here. Like at 49, it could be represented in another way. And if there's some things that just can't be broken down, then you might wind up with things like you can break it down to constant terms and variable terms. And then you can add together the like terms and making sure that you're dealing with only the same type of variable when you're combining, and knowing, of course, as well, that when you're dealing with squareds and just multiplying two different variables together, those are different variables, but you can treat them each just like you would treat x. So xy is treated the same way as it is x. They're both just numbers that are unknown yet. However, we can do arithmetic with their coefficients. All right, examples. Let's go ahead and do 2. Let's say we have 2x minus 7 plus y squared plus 3 minus x. We can look for our like terms. So I have an x here and an x here. Well, there's 2 x's over here and -1 over here, so I can say we have a just 1x left over. Then I can look at my y squareds. So y squareds are also just variables. I only have one of them, so I don't combine it with anything. It's just on its own still. There's no simplifying to do. And then here I have a -7 and a 3. Those are my constant terms. I can add them together and I get a -4. Here we no longer have copies or multiple terms that are alike. We'd have an x, a y squared, and a constant term. We cannot add those together, and so this would be fully simplified. Additionally, you could have like fractions here as coefficients. That would not change anything about how this problem is done. All it would mean is that when you combine, say, these x's, you would have to do, for instance, 4/3 minus 1, which of course would be 1/3, and this would be 1/3 x instead. Yeah, I hope this video has helped maybe clarify some things, and to just review what like terms are, why you must add the like terms and not mixing things like adding together like x plus or xy and x squared, or like x plus y, why you shouldn't add these together and just count how many variables you have, but rather why you must only add and subtract, combine the like terms. Very nice.